start. My plumber came right at the time class was starting. So trying to get my wife to answer questions for him. And so let's go ahead and get started here. First of all, we have a devotional presentation for the history of Unix. Which team member is headed first? Daniel Jones, Husin Kim?
It'll be me, Dashni Mohan.
Okay. Are you able to go ahead and share your presentation?
Yeah, sure.
Okay, great. Sounds great.
Oh, is it visible?
Yes, I can see it.
Can I start?
Yes, please go ahead.
So, good afternoon, everyone. The devotion is from Luke chapter 10, verse 25 to 37. So in this passage, we'll be seeing about the parable of Good Samaritan. So a quick summary of the parable. So an expert in law will ask Jesus, like, what should he do to inherit eternal life? So Jesus in reply will say, like, what is written in the law? The expert in law will reply, love the Lord your God with all your heart, with all your soul, with all your strength, and with all your mind, and love your neighbor as yourself. Jesus will reply, you have answered correctly. Do this and you will live. But the expert was not satisfied with Jesus' answer, so he'll ask again, and who is my neighbor? So now Jesus will summarize the parable of Good Samaritan. So in the parable, there'll be a man who is hurt, robbed, and left half dead in streets. So there'll be a priest and a Levite who will be walking past him but won't help him. Then suddenly a traveler, a Samaritan, comes up to him. He took pity on him, band-aided his wound, took him to the inn, took care of him, and took care of all the expenses needed to protect him. So after the parable, Jesus asked the expert in law, who do you think is the good Samaritan? Who do you think is a good Samaritan? So the expert will reply, the man who had mercy on the weak person. So Jesus told him, good, and do likewise. So from this, what I want to say is, during this coronavirus situation, everyone should help each other and be protective. Protect yourself and protect your neighbors by not going outside, and help the government too by not going outside and spreading the coronavirus thing, and obey the law. Obey the law. Love your neighbor as you love yourself. So anyone wants to add anything else?
So that was great.
Oh.
Nice message.
So
any other comments?
So can I pray now?
Yes, please do.
Loving Heavenly Father, thank you for giving us this good day. Help us to be safe in the quarantine time. Help us to be productive and finish our coursework on time. Guard us, guide us, and protect us. In Jesus' name I pray. Amen.
Amen.
So my topic is history of Unix. Oh, I have a question. Is my slide changing?
No, we're just seeing your screen with your overall PowerPoint presentation up, And so we see the devotion as the main one. And then on the slides side, we see your title screen off to the side in the slides, but don't see it as the selected slide, shall I say. Yeah, there you go. So now we see the title slide.
Is it changing? I'm like trying to see whether
Yeah.
these slides.
Yeah,
Okay.
so yeah, and if you want, you can do the slideshow, but right now you're just doing clicking on the side, which is fine too, and presenting your screen. So right now you've selected slide 2, which is your title slide, and that's what we're seeing.
I'm not able to do the slideshow. If I do the slideshow, it's not changing
Okay.
for the others to see.
Okay, good. That's fine.
So my topic is history of Unix. So Unix is a multi-user, multitasking operating system. The original name was UNICS, which is Uniplugged Information and Computing System, and it was later changed to UNIX, Unix. The first version of Unix was created in Bell Lab in 1969. The first version had PDP-7 along with few features. In the second version of Unix was developed in the year 1972, and then this is the part where it was the UNICS was changed to UNIX by Brian Kernighan. In 1973, the third and the fourth edition of Unix was developed, and it was rewritten in the language C language, which was the new language that time, and it was developed by Dennis Ritchie. Since it was written in a different language, they had the need to port it to a new machine. So after the third and the fourth edition, the fifth, sixth editions was released in next 2 years continuously, but for the seventh edition to get released, it took a while. So before the seventh edition could get released in 1977, Unix was used in like over 500 sites worldwide. In 1980, BSD 4.1 version was developed, and eventually they upgraded the OS in 1983 by adding Sun OS, BSD 4.2, and System V. After 5 years in 1988, AT&T and Sun Microsystem jointly developed SVR4, which is System V Release 4, which was in turn later developed into UNXWare and Solaris 2. After the 1988, the 10th edition of Unix was created, and later it was changed to Linux in 1991. So why Unix is popular? Unix is popular because it allows most Unix-like system to run the same application software and desktop environment, and the most common command used is shell or sh. Features of Unix: it's like easily portable, highly secured. If each user who's using the OS will have a separate user ID password, so it's secure. It's multi-user, so many people can use the system at the same time. Multitasking, many programs can be running at the same time without overlapping or causing any disturbance. Unix offer this feature of sharing files and restricting files. So if I don't want any of the user to see my personal documents or something, I can restrict them from using it. And the main admin or the root user has the capability to update or modify the kernel. And Unix has a built-in network. Disadvantages of Unix. The microcomputer user. For a microcomputer user, it is very difficult to understand. It has limited amount of application programs. It is not standardized, so an application program returned from one Unix system might not work with another one. Unix is not a user-friendly operating system. So these are my works cited. End of my presentation. Anyone have any question?
Thank you. Nice presentation. So have you used Unix a lot, or mostly Linux, or what?
No, I haven't used Unix before.
Yes. So it is a bit of a learning curve to use Unix and Linux for sure. There have been a lot of efforts. Yeah, there's a lot of efforts to make it much more user-friendly, but it's still a hacker's and a techie person's operating system in a lot of ways.
Mm-hmm.
Okay, so thank you. Moving on with the rest of the administrative stuff. Okay, so Daniel Jones, and then I'm not sure if Hyunsoo Kim will present or not because he went back to, I believe, Korea, but he's abroad, and so I'm not sure if he'll be able to join us online. So, and then the next one will be Ubuntu, and that's Jason and Bailey Livingston. So pretty straightforward. These are slides that you've seen already before. Wednesday, April 8th is the quiz due on Chapter 5, Process Synchronization, which is tonight. So that's by midnight tonight, the quiz for Chapter 5. And then next week, Wednesday, April 15th, is the quiz on Chapter 6. And Monday, April 27th, is the Chapter 10 Mass Storage Programming Problem. And then May 4th is the due date right before finals of the Chapter 12 extra credit programming exercise. And then we were covering virtual memory. Any questions about the administrative information before I move on?
Are we going to have a final or another like midterm?
It looks like the final and the midterm will be combined, most likely. And I haven't heard any guidance about finals in terms of it not being. So right now I'm making the assumption that we will have a final. If we don't have a final, we will have a late semester midterm. So how many seniors do we have? Because I guess they are eligible to not take the exam if this is their last semester. And again, that would be dependent if you're on the list, which is, so we have Ansel, I remember that, and Ian also. So if your grades and your grade point is of sufficient level, you may be eligible for not taking. And so that's Scott as well. So, and Jacob is the last semester as well. So are you folks, and then Joshua, okay, Josh. So are you guys in the midst of job hunting, or have you actually acquired jobs moving on here?
I have one lined up, but the course requirements are kind of screwing me over because all the testing centers are closed. So I don't know what my graduation timing is going to look like now.
Oh, wow.
Yeah, it's not.
That's difficult. So have you already been in contact with your advisor on what can be done and those kinds of things?
I'm emailing with the registrar and with my advisor, and I need to talk to my work, and yeah, it's all sorts of fun.
Yeah. Okay. Unfortunate. And so we have one student that's having internet connectivity problems, which is unfortunate. That's Daniel Jones. All right. So let's go ahead and move on to the presentation. Let's see. Actually, while we're here, I'm going to go ahead and share this with the attendees, although I don't think there's any much really new for you, but might as well since it's offering. And onto virtual memory. Okay, so we were looking at various page replacement algorithms. And so the optimal algorithm is to replace a page that will not be used for the longest period of time. For example, in this example below, let's see, 9 is optimal for the example. Oh, here's a reference string. I'm having to recreate exactly what this was to mean. But basically, the page replacement algorithm is if you know the page that will be won't be used for the longest period of time, that would be the one that you need to swap out. But of course, realistically, we can't read the future, and we don't know how all the processes are going to interact, and which would be the frame that would be the most efficient. But it is a measure of how of the absolute best performance you can get. So it's sort of more a benchmark item that tells you what your possible best case scenario would be. But of course, it is difficult to actually predict what page will be won't be used for the longest period of time. So not exactly practical in terms of implementation. The least recently used algorithm is the most popular algorithm. Make sure you know this algorithm well, and it uses the past knowledge rather than future. It says that the pages that were most recently accessed are most likely to be used again, and that's just from the nature of the way programs work. You can imagine yourself sitting in a loop, and you'll be continually accessing the same memory over and over again in a loop, or you're using software for a particular class or subsystem, and then that software will be utilized most regularly. And so it's saying that we're going to use the past history to try to predict the future, so that we figure any page that has been recently used has a high probability of being used again. So that's the justification for using the least recently used algorithm. And again, it is the most widely used algorithm for page replacement algorithm. It's most commonly used. So you basically associate a time of last usage with each page. Generally, there's a counter associated with that memory, that page address in the paging table. And generally, there's hardware support. Since it is such a common algorithm, a lot of times you will have hardware support for the least recently used algorithm. Here is using the example for the optimum. Okay, so this one was 9 page faults. That's what the 9 was. And using the same reference string, it's 12 faults. It's better than FIFO, which is I guess it was the same reference string from before. That's where I got off. There was no context. So it was the number of page faults was 9. So in this case, least recently used is better than FIFO, but worse than optimal, because everything is going to be worse than optimal, or at the best, the same as optimal, but in general, it'll be worse than optimal, the OPT replacement algorithm. So it's generally a good algorithm, and like I said, frequently used. Yeah, know this algorithm and realize that it's one of the most widely used page replacement algorithms. So a little bit of discussion, how do we go about implementing it? So that's where we're headed next. So I kind of mentioned this already, but the one common implementation is using a counter implementation. Every time a page entry, every page entry has a counter associated with it. And every time that page is referenced through this entry, we copy the clock ticks, or basically the clock time, into that counter. And so when a page needs to be changed, we just look for those counters, and we look for the smallest value, the one that has the least amount of time since last use. The downside of this is a search through the table is needed, and that means searching through the whole table. So this is certainly not optimal, and so other options are available. One form is keeping a stack of page numbers in a doubly linked form, and then when a page is referenced, we move it to the top, and this requires 6 pointers to be changed, but now you have a linked list that you can use. So each update is more expensive, but then there's no searching for the replacement because we have a linked list. And then again, there are also hardware schemes that use processes that periodically, like decrement counters, or provide options for quickly searching for the least recently used page, or the most, and the one that's been used for the longest in terms of replacement. And again, different techniques are used, and it would depend on what kind of hardware support you have for this algorithm, if you have hardware support. And then one thing to note is that LRU and OPT algorithms, page replacement algorithms, don't have Belides anomaly, and that's where the that there are reference strings that will expose a situation where the number of page faults increases with the increase of actual memory, which is very counterintuitive, but is possible. And in particular, we saw that with the FIFO. Actually, I had a student that asked me if I could provide an example of Belides anomaly, and unfortunately, I forgot to do that. So I'll have to defer that to another time. But just know that it is possible in a FIFO-Q, FIFO page replacement algorithm, but not in LRU or OPT. LRU or approximation algorithms, these are algorithms that don't quite implement least recently used page replacement, but is a reasonable facsimile of it, so that it is close enough to the LRU algorithms that you get enough of the benefits of the LRU algorithms. It needs special hardware, and it's still slow, but it is faster. So one is a reference bit. With each page, we associate a bit. It's initially set to 0, and when the page is referenced, the bit is set to 1. And then what we do is when we have to replace a page, we simply look for a page with a bit of 0, if one exists, and then we just use that page. So we aren't getting absolutely the page that hasn't been used for the longest period of time, but we get one of a group of pages that haven't been used in a while, and basically periodically on a periodic basis, the bits will be replaced back to 0, actually, because otherwise, eventually you could end up with all of the pages with a bit 1 bit and set to 1, and then you no longer can use this technique. So another option is the second chance algorithm. It's generally FIFO plus hardware provided reference bit. There's a clock that ticks, and that's basically where I was going. And the reference bit is replaced with a 0. And then every time we access it, it's sent to a 1. And so if the reference bit is 0, you leave the page in memory. Otherwise, you replace the next page subject to the same rules. So the second chance algorithm is basically a scheme where a page is given a second chance upon access. When it's been accessed, we then say, okay, we're going to go ahead and say that this page is going to get a second chance to stay in memory. And you can look at more details of exactly the ways that the second chance algorithm is implemented. I actually am not going to quiz you or test you on that algorithm, but just know that the second chance algorithm does exist. So here's actually, I take that back. There is a short question on the second chance algorithm. So here's the second chance algorithm in more detail. So here we go. We're going to prove the algorithm by using a reference bit and a modified bit in concert. So we take the ordered pair, whether it's been referenced and whether it's been modified. So modified says that we've modified this particular page since we brought it in from the hard disk. So in other words, if this gets swapped out, we will have to update the swap space or the temporary storage space on the hard disk. And then reference is just hasn't been referenced, is at least recently used. And so here we can look at an order of which pages would be the best to replace. So 00 means that it hasn't been recently used or modified, and so that would be the ideal page to replace. And then with the 0 and 1 case, it hasn't been recently used, but it's been modified, so it's not quite as good a choice, because even though it hasn't recently been used, it will cause a write-out to the disk. So the 00 would still be the best choice, but it is a candidate if all the rest of the pages are marked with 00. And then for option 3, it's recently used but clean. So then we can say, well, it's probably it's been used. Been used, but it probably won't be used again. But again, it's the number 3 choice on the list. And then the number 4, option 4, is it's been recently used and modified. Again, that is the worst case scenario. We'd have to write it out, and it's likely that we're going to have to bring it back in anyway. So that would be the worst choice. So here, just realize that with the second chance algorithm, that we have these ordered pairs of reference and modify, and keep in mind that case number 1 is the best case to be replaced, that it hasn't been modified and it hasn't been recently used, therefore it's the best chance. So this is, again, using the hardware reference bit, and we tack on a second piece of information, which is if it's dirty or not, whether there has been a change to the page since it has been brought in from the disk. So that's the second chance algorithm, is that if it actually has been a change on the disk, it may be given a second chance, or it's a second priority. Counting algorithms is keeping a counter of the number of references that have been made to each page. Not too common, but again, with the counter references, eventually you start running into problems with exceeding the storage space of the counter and things like that. But in which case you would have to re-baseline your counter. But again, that's not too common of a option used. And then least frequency used algorithm, it then replaces the page with the smallest count, obviously. The one that hasn't been used very often is the one with the smallest count, and so that one would be the least frequently used. And then another one is the most frequently used algorithm based on the argument that the page with the smallest count was probably just brought in and hasn't been used to yet. But again, most frequently used would certainly fail in the case where you're in a type loop accessing a data structure over and over again, and it's being used frequently, and it's still being used frequently. It could be a bad choice, depending on what particular algorithms and your usage patterns. So the other technique is buffering algorithm, page buffering, and that's where we keep a pool of free frames, and the frame available when needed. You can pull from the page. You read the page into the free frame and select the victim to evict and add to the free pool. So again, it's a pool of them. So there you know that there's always going to be an available free frame in your frame buffer, because periodically there's a task that goes through and adds to the free frame pool and chooses a victim to replace. And that would be using your page replacement algorithms, basically. It's possible to keep a list of modified pages and then write them when they're and then write pages out that are not write pages that are not dirty. So those are the ones that are least expensive to page out. So those could be possible candidates. And then let's see. The last point is if it's referenced again before reuse, there's no need to load the contents again for disk. And generally, so again, it's in the free frame, but it hasn't been reused, then there's no longer the need to load the disk from disk if it's actually applied to the same one. So those are all involved with the page buffering algorithms. Again, just note that these are algorithms that are available. I probably will not be testing you too much on the page buffering algorithms. In fact, I know I won't. So I'm going to stop my lecture slides here on this and come back to this. And I had an example that I wanted to present in terms of the page replacement algorithms that I will be asking you to become familiar with. And that's the least recently used, the FIFO, and that is probably the majority of the ones that I will be asking you to understand. So let's see. Oh, here it is. Where is it? And maybe I won't if I can't find it. Let's see. I had it all diligently prepared and now I can't find it. Oh, here it is. I put it in a default directory with the intention to move it to the appropriate place, and I actually didn't move it to the appropriate place. So here we have a spreadsheet, and we have a reference string, which is accessing pages 1, 2, 3, 4, 2, 1, 5, 6, 2, 1, 2, 3, etc. as you go down the column A. So hopefully you can see that. Oh, so I missed a question from chat. I see. Okay, so does this, Ian is asking, does this account for how recently it was created? And could you clear the page buffer when entering a new scope? So yes, certainly you could do that if you have the knowledge that I'm not going to be using my page, and you're saying, I'm going to voluntarily mark that I am free with my page and I'm a good candidate to have my page removed. Generally, that's not done because it puts extra load on the application programmer. So yes, you can imagine that would be done, but I have never seen that actually done because that adds, like I said, quite a bit of extra load on the application programmer. And in general, the idea of virtual memory is that the programmer should not have to realize that they're not, that the implications of the physical frames, they just need to work with their logical pages or even just their logical memory, and the pages are being handled for them as well. So in general, you don't want you have your application programmer have to deal with that complication. And since I didn't answer the question right away, Ian, could you update me on what I was talking about when you said, does this account for how recently it was created? Is that the page in terms of buffering, page buffering? So I can go back to my presentation. Let me go back and see with the page buffering. Okay, so Ian is saying that the question was actually answered. So, all right, so let's go back to our example. Again, the key thing that I want you to get away from that is that page buffering algorithms exist and are possible. Since they are not commonly used, I'm not going to really hold you to that. I want you to understand the optimal, the FIFO, and the least recently used. And we will probably be doing some exercises on FIFO versus least recent use as examples. So again, here we have column A with the page reference strings. And then we have, in this example, I have 4 frames just for ease of use. You know, it wouldn't be a very capable system that only had 4 frames, but it's easier for us to understand. So with this page reference string, we'll go through an example of how you would actually check how many page faults happen and what actually is which pages are in which frames as you go through this algorithm. This is also a good example of doing a code walkthrough where you're actually simulating what does the compiler do and what does the computer actually do at each step of the phase, at each phase of your algorithms. And this is useful actually for debugging your code. Even it was widely used before the advent and the prevalence of debuggers, but it's still a valuable technique. I've helped multiple students who've come into my office with questions not only about my classes, but of a program they're doing from another class. And generally, as we walk through the problem, a student I'll be walking through it with them, and they say, okay, now what happens next? And then he'll get to a statement, and they're just using their overview of the high level view. They'll say, oh, this happens next. And I said, so walk through what is the computer going to actually do here? And all of a sudden the light bulb will come on and say, oh, wait a minute, it's doing this. So this is where my error is. It's not doing what I had envisioned when I put down the high level language statement, but as I walk through what the CPU and what the computer is actually doing at this stage, I can see where my mistake is and what needs to be corrected. So again, this is a great technique that can be used independent of page replacement algorithms, but we're going to be using it for page replacement algorithms. So we have the FIFO scheme. And so we can see here on row 3 that the page reference is 1, and all 4 frames are available. So we're going to put it in frame 1. Actually, in actuality, this would be frame 0 because we do 0-based things, but it's just easier for us humans to deal with 1-based things. But in coding, it's generally easier for 0-based things. But anyway, that we put it in frame 1, and then we can see here in the queue we have 1. So we have actually had page 1 come in. Likewise with page 2, 3, and 4, we have the page faults in column F add up 1, 2, 3, 4 because each of those are brand new pages into memory. And then we can see that in the queue we have 1, and then 1 followed by 2, followed by 3, and then eventually the queue ends up with 1, 2, 3, 4. Then we reference page 2, and page 2 is already in frame 2, so there is no page fault there, and so there is no update because we're just doing it FIFO. And then with 1, again, that's already a memory, so there's no page fault there. And so our queue remains 1, 2, 3, 4 because we're keeping track of basically the order that the pages came in to the frames, the physical memory. And so then we can see here we have a page reference of 5, and that's new. And so then we look in our 1, 2, 3, 4. So the first one in the front of the queue is 1. So we put 5 in frame 1, and then 2, 3, 4 stays the same. And then we get another page fault. So see here, 1, 2, 3, 4, no page faults in the next 2, and then a page fault in the reference to page 5. And that is put into the first one, and we take 1 off the queue, and then we put 1 at the back of the queue because that is the brand new page that has been brought in is in frame 1. Likewise, when we do 6, that again is another page fault because 6 is not in there. And we look in our queue on row 9 and see that frame 2 is the one to be replaced. So we do that, replace frame 2 with the 6 in C9, and then 3 and 4 remain the same. And then you can, as you go through this example, and we are running out of time, and so we'll go through this example again next Monday because Friday is off. It's Good Friday. We can go through this example some more. But any other questions regarding the material or the class schedule or what's going on? All right. Well, I will go ahead and let's see. I've got 3 minutes. I think I'll go ahead and just go through this particular problem again. There are a lot of quizzes listed in the gradebook that aren't given dates. Okay. In particular, oh, yes, I am. The quizzes that don't have dates, I'm actually waiting for me to cover the material first before I set a date for the quiz, especially since some of the material won't be covered. For instance, in all actuality, the one on the deadlocks, we just raced through that, and I would not probably put you through a quiz on that unless we went through in a lot more detail than I went through it there. The key thing to note from that is that in all practical purposes, deadlock prevention is not done, that it's just lived with because the solutions tend to be worse than the problem, so they're not done. So that's the key takeaway from that chapter, but we won't likely have a quiz. So yeah, the ones that aren't listed in the gradebook with dates are TBD. It depends on if we cover it, and if we cover it in sufficient detail, in my opinion, for it to be there would be a quiz on it. For instance, the virtual memory quiz, the virtual memory quiz we'll probably put on the board once we get through the material. Any other questions? Or did I not answer that question is the other thing. All right. Well, have a good Friday. Enjoy your time off, and I hope you have a good online Good Friday service that you're able to view. There are lots of them out there. And with that, I'm going to go ahead and turn off the recording. And if you'd like